G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. This is lecture 3. So we're just going to go over a bit of revision of supremum infimum, and we're going to talk about real space. This one's split into two, part A, part B. So let's get into part A. So just looking at real space in set theory, real space, capital R, refers to all the real numbers, which include all rational and irrational numbers. The set Rn now just the typing and the letters. This should be a little n, but every time I tried to capitalize this R, this n went to capitals. So sorry about that. That should be a little n. The set Rn consists of all n tuples of real numbers R. It's called the n-dimensional real space. An element of Rn is thus an n tuple and is written x1, x2, dot, 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 up to xn. And I know the question you're going to ask is, what's an n tuple? I'm glad you asked. It's an ordered set with n elements. So that's all it is. An n tuple is just an ordered set with n elements. Just a phrase. So don't get too hung up on that. Properties. So there's two main properties for real space. Component-wise addition and scalar multiplication. So they're things that occur within real space. You've got to have some addition and you've got to be able to do multiplication. Once you've got that, that makes it a real vector space. So you're doing these with vectors and sometimes with matrices. So you're in component-wise addition and scalar multiplication. That makes it a real vector space. And I've just written another note. Every n-dimensional real space is isomorphic. There exists a bijective function of one-to-one and onto mapping. You can go back and look at the images from, I think, lecture 1, where I put the images of those two. If that's not clear in your brain, I do want to put them in again in this lecture. So that's between them, that preserves the structure, and then I've got to it. So you've got to read that. Every n-dimensional real vector space is isomorphic to it. And then there's a sort of an explanation in there. Second point, but main point is the black part. Second point, just move the image out of the way. There's a dot product, sum of the term-by-term product of the components. So this makes it an inner product space. And again, just using words there. And the thing you want to know is there's component-wise addition and scalar multiplication, and there's a dot product. You can do a dot product. So that makes real space. That's, if you've got things that can do that, then you're in real space. So they're your two things. Okay, let's look at a question, because questions, I think, clarify heaps of things. And you'll find that with your students as well. You give an example and they go, oh, I get it now. Don't you love that aha moment? Okay, describe the following real number sets mathematically. So these are pretty easy. Set of integers, set of positive real numbers, set of real numbers between 0 and 1, and notice here I'm using round brackets, so it does not include the 0 and 1. So set of integers, you can either write dot, 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 -3, -2, dot, 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 1, 2, 3, dot, 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 so the dot, dot's extending to infinity, or you can write it sort of a bit more professionally. X is an element of Z, so they're the integers where you've got X between -infinity and infinity. So that looks a bit better. That will still get you full marks. Set of positive real numbers, so X is an element of the reals and X greater than 0. And notice I'm using curly brackets here for sets. And X is an element of R where X is in between 0 and 1. So again, pretty straightforward. Next thing, supremum. The supremum, and again, we look at this very briefly on a single slide in lecture 1. So this is giving you a bit more. The supremum or least upper bound of a set S, which is an element of the reals, is bounded above, is an upper bound B, and I've made this little b, which is an element R of S, such that B is less than or equal to U for any upper bound U of S. That's great, Dr. Everett. Thanks for sharing. We use the notation sub S for supremums. So B equals sub S, and that's B being the bound that I've just created here. There's two defining properties for sub S. It's an upper bound of S. That's pretty obvious. And it's smaller than or equal to any other upper bound of S. And I'll explain that with examples. I did try and explain it in lecture 1. I'll do a more detailed explanation here. Hopefully it'll be more clear. The infimum or greatest lower bound of a set S, which is a subset of R, is bounded below and is bounded below, well, sorry, which is bounded below is a lower bound B of R of S such that B is greater than or equal to L for any lower bound L of S. So we use in notation inf S for infinums, so B equals inf S. Two defining properties, which are effectively the reverse of the supremums. It's a lower bound of S, and it's larger than or equal to any other lower bound of S. So examples will help clarify this a lot. So S equals 1, 2, 3. Pretty sure I used the same example in lecture 1. What is sup S and inf S? Really, really easy. Supremum is 3, infimum is 1. Hopefully straightforward for your brain. What is inf S and sup S if x is an element of the reals where you've got x squared less than pi? So now we're looking for what is inf S and sup S. So we're looking for a real number. And we've got to be careful. We're doing x squared is less than pi. And what is pi? 3.1415. And how many decimal points do you know? Okay, so here we've got the supremum is root 3. We want a real number which is going to work here to give us a number less than pi that actually exists. So supremum is root 3, infimum is minus root 3. So they actually exist as the supremum and infimum in the real number plane. You notice here we can't actually just give a decimal point. We can't sort of say, well, that's 3.1415. I can't actually say, okay, I'm going to make x the square root of 3.1414, which is obviously a number less than pi, and I can't say that's the square root of that number because it's not going to be true. Because you can then add another single decimal point at 0, or 1 on the end and still be less than pi, and therefore it wouldn't be a supremum or an infimum. So you've got to actually give a number which is valid within the reals, which you can't create another one closer to it. And because root 3 is the closest real number, that classifies as the supremum and infimum. It's a little bit tricky. And hopefully this will make it even more clearer or more tricky. So what is it if x is an element of Q? Okay, so now we're instead of reals, we're doing Q. So we want rational numbers now. So forget root 3 and minus root 3. The infimum's null, since we can always go one decimal place closer. However, so they're both null. The supremum's null, infimum's null. I'm going to move my image out of the way because we're going to get some stuff down here. However, since pi is 3.1415 and the root is 1.77, so if you do the square root of 3.1415, you end up with 1.77. Oh, I can't remember the rest, 1 or 0. It's not smaller number there. Okay. The root is that, so we'll just stick to 1.77. You can now think, okay, an upper bound, not the supremum infimum, an upper bound is 1.8 and the lower bound is minus 1.8. So this is like where you've got those graphs that go, you draw a graph and it goes almost touches 1, doesn't quite touch 1, and you say the limit is 1. Well, we can say or if going to 1.8, the limit is 1.8. Now that's outside the range. That will give you a number greater than, but we can say that's an upper bound. It will never get to that bound. Similarly to the graph, it will never get to 1 on the certain graphs. Okay, so we could say that is true. So now something for your thinking caps. So this could be regarded as a supremum infimum if we limited our answer to one decimal place with a reminder that the upper bound and lower bound does not have to be an element of the set, and neither does the supremum and infimum. So here's food for thought. Let's consider 1.7 and minus 1.7. Can you declare them as supremum and infimum if we're limited to one decimal place? And I'll leave that for your brains to think on. And so thanks very much, Dr. Everett. Appreciate that. And I was just drawing a diagram there. Okay, question 4. Okay, so we want to let A equal n plus minus 1 over to the n over n, where n is an element of the naturals. We want to compute sup A and inf A if they exist. So solution. So since this, which is effectively 1 over n, which is obviously less than 1 because it doesn't matter what n is. As soon as n gets big, this just becomes a smaller and smaller fraction. For all n, which are elements of the natural numbers, where n is not 0, so our natural numbers are, in this class, we're counting 0 as a natural number, but we're declaring here that we're not including 0. So since we know this is true, right, we know this equals 1 over n, which is going to be less than 1. We can then say, now we're going to use this here, we can use n plus this. We can say, here's the equation, that's going to be greater than or equal to n minus this, so the minus 1, so n plus this is obviously going to be greater than n minus this, and that's going to be obviously greater than n minus 1 because we've just determined here that this is less than 1, so this is always going to be greater than n minus 1 for all n where n is less than 0. So consequently, the set A is not bounded since n is unbounded. So this will just, you can't get a bound on that. So therefore, sub A doesn't exist. That's the first thing. On the other hand, you can still use that inequality. So we're just going to use this inequality up here, where you've got the greater number. So we're not using this one or this one. We're using the biggest one, which is this biggest value. We can see that that is greater than 0 for all n as elements of the natural numbers. This is always going to be greater than 0 because this number, whether it's positive or negative, if it's the 1 or to the 2 or to the 3 or whatever, will oscillate between positive and negative. This will always be greater than 0 because this value can never be greater than this value. So this is always going to be positive. So since we've always got that positive, it's always greater than 0, and that's the biggest thing you can get. It's not the smallest, it's the biggest thing you can get. Therefore, 0 is going to be a lower bound. So we can say that, or we can see that, or we can say that inf A equals 0, since 0 is also an element of A. Okay. So there's a question you could work through and see how that works. Here I'm just using the question, using a negative of the question, and then saying that that's greater than n minus 1 because we've here declared that this is obviously going to always be less than 1. And here we can see that the whole thing is always going to be greater than 0. Okay, here's some questions for you to do while you're waiting for part B to show up. So that's it. There they are. I'll put them in the notes. The answers will be in the notes as well, but these are fairly straightforward questions that you should be able to figure out. God bless you. Stay safe. Go and have a hot chocolate, coffee, drink of water, do some exercise. God bless you.